Now I am recording the video. Anyway, like I was saying, this is how we define them. Okay. So then the question becomes, how do I actually compute with this? And this is going to require that we remember that ds dt, what's ds dt equal to? S of t is the integral from a to t of the length of x prime of tau d tau, because it's the length of that vector. So what's the SDT? Length of x prime of t. Now we can use the engineer's trick. Let's just multiply both sides by dt, because man, it would be nice if there was not a ds here, there was a dt I could use instead. So ds is, this is actually why we do this after the change of variables, right? The idea here is that the relationship between a unit change in the arc length and the unit change in time is given by how fast the particle was moving. So you think about, this is the distortion factor that tells you the relationship between change in time and change in arc length. Okay, and so that means we can define the scalar line integral. So this is a definition. The scalar line integral of f along x is the beautiful symbol on the one hand that shows all the intuition about what's going on, and on the other hand, the computational formula, the integral from a to b of f of x of t, length of x prime of t. I'll write it higher on the board. I'm sorry, guys. This is worth writing again, so I'm not being all cramped up down here. What I said was the integral of x of f ds, which you should think of as representing the Riemann sum, and then the computational version, the integral from a to b of f of t, x prime of t. So the theoretical construct and the computational version. If you like, you can think about this as this is parameterized by arc lengths, which means that it doesn't matter how fast the particle is traveling. This is parameterized by time, which means you're incorporating the motion of the particle into it. Okay, so how do these things show up in practice? An example. Let's let path be equal to, or say that the path is going to take 0 to 2 pi into R3 by x of t is equal to cosine t, sine t is t. So it's the helical path.
Is that R3 or R2?
R3. And let's integrate the function x, y plus z along that path. So f of x is equal to x, y plus z. Find the integral over x of f. Yes. And this really is where you want to think about these things as density functions and not surfaces, right? In 3 dimensions, if you have a 3-dimensional domain, you think of this as a surface. It's really something that exists in 4 dimensions, and I don't want to do that. I want to think about this is the path you're traveling, and what f is doing is assigning to every point on that path some kind of density, and I'm adding up to the total mass or total charge instead. Okay. So how do I compute it? Or if you don't care about intuition at all, which you probably should, but if you don't, you just literally look at the formula for how to compute this thing and write a bunch of crap down. Right? What do I need to do in order to do this? Well, I better know what x prime of t is, which is minus the sine of t, cosine t, 1, And I better know what the length of x prime of t is. And boy, oh boy, it sure seems like really coincidental that we keep getting the helix over and over again because its length turns out to have a cosine squared and a sine squared inside of it that disappears. So you get the square root of sine squared t plus cosine squared t plus 1, which is root 2. Okay, so there's that. And so what we're being asked to do is the integral from a to b of x, y plus z times the length of x prime dt. What are a and b? 0 to 2 pi, because they tell me where the path starts and where the path ends, right? Those are t values. So this is the integral from 0 to 2 pi of x, y. How am I going to integrate x, y, and z dt? Oh, that's right. I just substitute in, right? I've got an expression for x, an expression for y, an expression for z. So these are like bookkeeping exercises and you should confuse them. So this turns into the integral from 0 to 2 pi of cosine t, sine t, plus t, all times root 2 dt. Now, I'm going to go one step further with this. I'm not going to finish it. I'm going to leave it to you guys to finish. Because I think this is a calculus. This is like a calculus 1 integral right here. I'm going to use the math book's favorite, every calculus book's favorite identity to say that I don't want to do a u substitution. I'm too lazy. So I'm going to replace that with a sine of 2t. This is the integral from 0 to 2 pi of 1/2 of the sine of 2t plus t times root 2 dt. And from that point, I'll leave it to you to finish. You don't have to do this, but this identity is nice. Okay, so that's basically what the deal is with line integrals. Line integrals are about substituting in and realizing that what you're doing is a scalar integral, right? A scalar contribution. You take the path, you chop it into pieces, and it's a scalar contribution. So an area-like object. So a more interesting type of integral, and one that people have spent less time with, is what happens if instead of a scalar field, I want to think about something more related to force fields instead. What if I have a path going through a vector field, and I want to know how much of the vector field is pressing on the path, pressing on the particle moving through? So the idea there is you start with some vector field. This is going to be called a vector line integral. So that was a scalar line integral. Now we're going to do a vector line integral. The picture here is you have some kind of vector field. Oh, there's a vector field. There you go. There's a vector field. And then you have some path that goes through the vector field. And the idea is, if suppose that this is the path of an electron moving through an electric field, the idea is how much force is acting on how much is the force acting on this particle as it slides through the field. So the natural thing to think of here is that vector line integrals originally came up in the context of work. Is there the first place where vector line integrals were invented is in the context of work. So think of as being contributions of force against a moving particle. All right, so I got a question now, which is, suppose that at this point right here, I freeze the particle right there. That point right there is x of t naught. How much of the force field is the particle feeling at that point? Well, so Jack said dot product. Dot product of what? How do I compute this, right? So what direction is the particle moving? Let's say we go this way. What like in a vector analytic context, how do I describe how that particle is moving as it slides along the path? What object describes both its speed and its direction? It's derivative, right? Okay, so there's some derivative vector poking out this way. At that particular point in the curve, the force field is poking over here like this. So how am I going to do that? How am I going to figure out how much that force field is acting in the direction of motion? How do I do that? What tool do I have? What mathematical tool is it that does that? Projections. And projections are built out of dot products, right? So the idea is that this relationship, the relationship between this force and this motion, is going to be determined by the dot product between these vectors, right? So for a vector line integral, we're going to have dot products involved that measure the relationship between how the function is moving and how the force field is interacting with it. Okay? Because remember, what a dot product gives you is not just the angle between things, but also how much contribution there is in one in the direction of another. Remember, we did projections. All of you guys that said projections, the idea of projection is that you have a vector pointing this way and a vector pointing this way, and you say how much of this vector is in that direction. And so the idea is we want this vector to be the vector of motion, and we're going to project the force vector down onto the direction of motion. Okay, so if this is the force vector, we're going to drop that down to look at the direction of motion. What? Door's not open. I can't see the guy rolling around on the one wheel inside the hallways. It's like my highlight of every day. Okay, so here's the definition, and we'll see if we can untangle what's going on. Okay, so this is the definition. So the vector line integral defined like so. So when I write capital F here, I want you to think of a vector value function. So this is a vector field. F has to be a vector field. So it's a function that assigns to each point in the domain a vector of the same type, from R2 to R2 or R3 to R3. And the way that you think about a vector field is exactly like this. To each point, X, Y is attached to vector F of X, Y. Okay? Vector fields attach vectors to points. If you suspect that curl and divergence and gradient are going to start coming back into the picture here, they're going to. All right, along a path X from T runs from A to B which is denoted, okay, you got to be a little bit careful here. This time, the way we're going to denote this is like this. The integral over X, now we're going to write F dot ds instead. And we're going to extra emphasize the fact here that we're thinking about vectors by making sure that our ds quantity is also a vector quantity. ds without a vector was a scalar quantity. ds in the other context was ds is equal to this. This is the scalar quantity. Okay. Here, this is considered to be a vector quantity because I need to somehow make this vector and this vector interact with each other. Any guesses, by the way, what this is going to turn out to be? Integral from A to B of f of x of t dotted with not the length of x prime anymore, but actual x prime. Because that actually keeps track of what the function is actually doing. This is the velocity of the actual velocity of the function at this point. The velocity of the path there. Okay, so this is a dot product. This quantity is the quantity that we think of as ds vector version. It is really easy to get these confused, but what I want you to think about what's going on here is you are measuring the interaction of the force field with the direction of motion. Right? So for example, if we think about something like this, suppose you've got a constant vector field. And you cut through it with a path that looks like this. There's x of A. There's x of B. Does the vector field act on the motion of this particle along this path? Why not? Because any motion of the path is in this direction. Velocity of the path is in this direction. The force field is acting in this direction. So there's no interaction between the force field and the direction of motion. So this dot product would be 0. In this context, f of x of t dotted with ds, 0 for all t. So if your professor was a total bastard and wanted to ask you a conceptual question, and they wrote down that picture and then said, tell me what the integral over x of f dot ds is equal to. Well, you're integrating 0. What's the answer? Some constant. Not 0, but some constant. I mean, the idea is that like it's whatever the it just nothing changes, right? It's a constant contribution. Yeah. So the way you should, so from a physical standpoint, what you should think is if this was an electric field and you had an electron like moving down this path, what acceleration would the electron feel in this linear path corresponding to like the electric field? And the answer would be it wouldn't experience any acceleration due to the field because its motion is perpendicular to it. Right. So I apologize for all the physical metaphors here, but these are really easy, much easier to understand if you have something to link them up to, right? I mean, the symbol itself makes sense even without having a physical underpinning, but this is what this is for. This stuff is for this kind of mathematics. Okay, so let's do an example of one of these guys, or at least set one up here. Actually, before I do that, let's make it absolutely clear what the physical interpretation of this is. Make it completely crystal clear. This is what any physicist and any applied mathematician and any sort of like engineer working on applications would say. If F is a force field, then the integral over x of f dot ds is work done by F on a particle traveling by X. It's literally work. In fact, they probably could have just told you this in the very beginning. So this is what, the third or fourth time you've seen work introduced probably in all these classes. Like the first time, work is equal to force times distance. And then they beef it up a little bit and they say, oh, well, really, work was equal to F dx instead because like, you know, like force could vary over the course of a thing. And then in 241, they say, oh, no, actually work is equal to something like this, but in 2 variables where they don't give you the full version of the formula, right? So this is basically, this is the real version of the work. Okay. All right, so let's look at, I'm just going to set this up and not actually compute it because these are pretty easy. They compute in exactly the same way. So if F is equal to X, Y, Z, what does that do? F is a vector field. What does it do? Draw a picture of that in your head. What does it look like?
Goes out for zero.
Yeah, and the further out you get, the bigger the arrows are, right? So it's like exploding away from the origin. Near the origin, the arrows are small, and the further away you get, the bigger the arrows get, right? So it's accelerating away from the origin is one way of thinking about what's happening. And let's let x take 0, 1 into R3 by x of t equal to t 3t squared 2t cubed. Then, I think that the intuition is prettier than doing the examples, but since we have to do things in the real world, it's occasionally important to show that these things can be applied. 1, 6t squared is x prime of t. So if you want to actually write down the integral of x of f dot ds in its computability formula or its computable formula, then you write down the integral from 0 to 1 of f composed with x, which is t 3t squared 2t cubed, because this is f of x. And then you dot it with ds, which is equal to the derivative vector. Now it's just a standard dot product, right? If you're doing one of these questions and you accidentally end up with a vector left over before you integrate, you did something wrong. This has to reduce to a scalar. These integrals all produce scalars. I think this actually turns out to be 7. I didn't do that in my head. We'll just hold the equal to 7. So the next step here, if you were actually computing this yourself, and I won't go any further than this, is actually to compute this dot product. So t times 1 is t, and 3t squared plus, or times 6t is 18t cubed, and 2t cubed and 6t squared is 12t to the 5th. And you just use standard integration. Okay. All right. Okay. So finally, let's talk about. So here's actually, I'll give you a couple of alternative versions of this. So here's an important idea. So another way of writing this, another way of writing the integral of x over the path of f dot ds is actually to rewrite this as f dot the unit tangent vector t and then ds without the vector on it. Now, from a physical standpoint, that should make sense because what we're doing here is we're saying, okay, ds cuts the path up into little pieces. T keeps track of the direction that we're moving, and t dot f that encodes how much of f points in the direction of t. Okay. Now, if you want to know why that's true, remember that ds is equal to x prime of t dt. But if I wanted to, I could write this as x prime of t over the length of x prime of t times the length of x. I can uncancel the length of the x prime of t. And if you remember the definitions, this is the definition of the unit tangent vector. That's t. So this is t, and that is scalar ds. So this gives us a way of sliding back and forth between thinking of this as a vector value ds and a scalar value ds, which is often useful in interpretation. And that gets us this picture. So we think here's x, here's f, and I think of t is poking out this way. And then f dot t, because this is a tangent vector now, because this is a unit vector, you can actually think of the projection as, let me get a different color. Instead, let's make f point more like this. This is f, then this vector right here this is now, the reason to do this, to think about the tangent vector, is because now this is literally the projection. Right, so this vector right here, this blue vector, this is f dot t. This is the natural picture that you want to draw when you think about this. Right, so it might seem like a bunch of fuss over nothing to take this and rewrite it like this, but it's much easier geometrically to see what's going on if you have this picture, I think. Okay, so now let's start linking this up with, so the big idea is that like, there's a connection here between like vector fields and this theory of integrations, this theory of work, for example, or theory of contributions. And so we might expect that we can actually study vector fields with these ideas. And so the first one we can think about is, we can talk about an idea called the circulation of a vector field. Okay, so circulation is defined in the following way. Suppose that X is a closed curve, closed path. So what I mean is, what if X goes back around on itself like this? So X of A is equal to X of B. So the path ends where it begins, closed path. That's what I mean. Then, let's see, in that case, the integral of f(x) dot ds, this vector field, the contribution of the vector field along the path, this is called the circulation of f along x. And we can try to imagine, let's see if we can intuitively figure out what it is that it means. What are we measuring when I say that? Why call it circulation? And the easiest way to think here is make the assumption for a second that F represents the velocity of a fluid. Right? So to make this like why we're calling this circulation, imagine that F represents circulation of a fluid. Then what are you doing when you compute this? Well, you can imagine that at any point you have this vector, which is t, and you have some velocity of a fluid, which is F, and what you're computing at any point is this vector right here, which is F dot t. And what you're doing is you're taking that picture and you're moving it all the way around the loop until you come back. And you're basically adding up, as you go all the way around this loop, you're adding up how much the fluid has been pushed. Velocity basically translates into displacement, right? So this is keeping track of something about the displacement of the fluid around this loop that you made. I don't know if that analogy makes sense to you. But that's basically the idea. It's like you can think of it as the amount of fluid that moves tangentially around the closed loop. And it's called a circulation because it's closed. Right? So in some sense, you're measuring, we're going to link this up with the idea of curl eventually, right? The twisting or rotation of a vector field. The idea is that what circulation is measuring is, what does it look like? You know, what's the total amount of fluid that's sliding around this thing? In some places, it might be moving faster. In some places, it might be moving slower. In some places, the direction might reverse. But as you go all the way around, what you're going to measure is something like the total amount of fluid that looks like it's being pushed around this particular like two-dimensional loop cutting through three-dimensional space. Or one-dimensional loop, sorry, one-dimensional loop through a two-dimensional space. So I need to, okay, I'm trying not to devolve into jargon here. Does this make sense what I'm saying? But I also don't want to like repeat it so many times it turns into just I'm up here saying static. Or the famous thing that one student told me one time was they hated when professors explain things so much, they explain all the way through understanding and out the other side. Like, I don't want to crash through the barrier and confuse you by saying too much. The point is what this measures is each incremental thing here, remember, like measures a little bit of fluid pushing on a little bit of curve. And if I add it all up, all the fluid that's moving all the way around, I get a sense of the total amount of fluid moving through the path. Okay, So this is going to turn out to be connected to the curl of the vector field eventually. Okay. And I want to point it out here because this is another like one of these really strong physically motivated ideas that gives us a way of actually studying vector fields. One way of studying a vector field is to look at a bunch of different loops and look at the circulation through a bunch of them. This comes up in applications all the time. Draw a bunch of circles and see how much fluid is flowing on each circle. So this is one of the ideas that shows up a lot of times in systems where like fluid dynamics, study of water, study of gases, gas flow. Yeah. All right. I don't want to. I'm actually out of time, so I don't have anything else to say today. But yep.
So this mentioned my fluid that's going up around the circle, or
It's around the circle. No. Okay, so those of you that have seen the future, eventually we're going to be able to connect the amount of fluid passing through the boundary to the amount of to something going on in the interior. This is like Stokes' theorem and Green's theorem and the divergence theorem, if you've seen them in the past, are relationships between something happening in the boundary and something happening on the inside. And so it's a good question. This just talks about what happens on the edge, but there's a beefy theorem that tells us that there's a relationship between what happens on the edge and what happens in the interior. So you've seen the future. All right.